and thanks for invitation. I'm very happy to be here. And let's see. So in this mini course, I will talk about the measure rigidity in the higher rank group action. So I will let you know what is the higher rank group for me very soon. But I want to start with some example, or theorem. So for me, throughout this mini course, I only want to think about SL and R. Maybe you can think about other Lie groups, but right now, let's just think about SL and R. And then higher rank actually really means that n is only 3. Sorry. 2 is too low. And if you remember the rank of the group, I think we saw the definition of the rank at some point. And that means that the rank of the group is rank of the SL and R is n-1, and higher means that it's bigger than 2. So, and I want to think about the lattice in G, which is that we recall that the lattice is discrete subgroup with finite covolume. So if you have a co-compact discrete group, then this will be the lattice. But of course, I will not give you the example other than SL and Z. But keep in your mind that there are really a lot of lattices in SL and R. So what I want to do with this is that if you see the surface group, if you think about SL to R and then co-compact lattice, then they are all surface group, right? And you saw in previous lectures that the surface group is somehow not rigid in some sense, flexible. But in this case, if you go to the SL3R and the lattice, then actually it is very rigid. Even it is super rigid. So I want to start with the theorem. Nowadays, it's called the Margulis superrigidity theorem. And I will not write down the full generality. I only want to write down that when gamma is SL and Z, n is only 3, then the gamma is somehow super rigid because if you have any homomorphism from here to gamma to SLMR for any m, so for safety, let's say PGL, then there exists rho tilde from SLNR to PGL-MR, which is the homomorphism. And let's see. So I want to, after this theorem, I will ignore all the finite index and finite error. But let's just write down the statement more accurately. So there is a finite index subgroup such that rho of gamma is same as rho tilde of gamma for every gamma in gamma prime. So basically, there is no deformation, or there is no, basically you can classify every representation. So if you have if you think about SL and Z as a just abstract discrete group, then there is no reason you can expect that your representation extends to the envelope SL and R, right? There's no reason. However, Margulis told you that your representation is actually have some algebraic origin, which is coming from the representation of SL and R. And you may believe that representation of SL and R to some Rm is algebraic because you can classify using the Lie algebra.
Are you assuming that the representation has a discrete and flexible image?
No. That's another point of the statement. You do not assume anything. You just have any homomorphism that really comes from here. And then actually this will give more additional information that the Zariski closure of the image should be semi-simple or something like that. So I do not assume anything. This is just homomorphism.
So it is more special to the SLNZ. I mean, in the general case, you may have a representation for the images inside the unitary.
Yes, exactly. Yeah. So that's the reason I only write down the SLNZ. Yeah, because this is general for any lattice in higher rank simple Lie group, but especially for the co-compact lattices, there may be some error.
Yeah. Thank you.
But SLNZ, there will be no error. So. Okay, so now maybe also another question is that I'm thinking about the homomorphism, but then now you may ask that why don't I put the assumption like faithful, right? So maybe I can write down here one more theorem. You already saw the statement before, I guess. So again, this is Margulis. Now it is called the Margulis' normal subgroup theorem. So if you have a gamma is again SLNZ, and is only 3, of course this is not all, this is true for general situation, but let's just focus only on the SLNZ. And now if you have a normal subgroup, so the condition about the faithfulness of the homomorphism is about the normal subgroup, because it is about the corner. So now if you have a normal subgroup, then either n is finite or it has finite index. So of the finite index, I can just ignore the faithfulness. So if you have a homomorphism, then your corner is either finite or finite index. So if you have a finite index corner, then basically the homomorphism is trivial. Otherwise, you can go to the finite index, and then you don't need to worry about the faithfulness. So this is really about some group theoretic property. But then now you may have some questions. Now I know that I can classify all the finite dimensional representation. If you have a surface group definitely or free group, then I cannot really classify all the representation, a finite dimensional representation. But if you are in the higher rank, then the group is complicated enough so that you can classify all the finite dimensional representation. And the next question will be, how about the infinite dimensional representation? And if you are interested in the unitary representation, then that's Roman's mini course. But now I want to think about the different infinite dimensional Lie group, which is the diffeomorphism group. So how about the diffeomorphism group, valued homomorphism, and then for me, manifolds are always closed. That means the compact, compact without boundary, and smooth. So now, can we expect some similar phenomena like this? So because the SLNZ is quite complicated, so your diffeomorphism is basically the symmetry of the manifold. So if your manifold has complicated symmetry, then there should be some rigidity, right? Because unless either rho is trivial, or if your symmetry of the manifold contains some complicated group, then we may expect that it should be rigid in some sense. So for instance, this was called the Zimmer's conjecture, and now this theorem. Let me just write down the theorem in there first, in this direction. So the theorem by Brown, Fisher, Hurtado is the following. So let's say gamma is SLNZ again, with n is only 3. Then if you have a, now I want to write down alpha. Let's say C infinite diffeomorphism group. So if you have a group homomorphism from gamma to diffeomorphism group of M, where M is again the compact, smooth, without boundary manifold, and then basically this is same as you have a gamma action on M. And then now if you think about the Margulis superrigidity, then you can easily see that if your M is very small, so for instance, your gamma is SL 1 billion Z, and your target is just PGL 3R, then there is no room for the SL 1 billion R, right? So it should be basically there is no non-trivial homomorphism. And the analog theorem is like this. So if you have a group action on the manifold, but now if you assume that dimension of M is M minus 2, then the image should be finite. Actually, this means that of the finite index, you will get the trivial action. So now you can compare the theorem in the Margulis for the finite dimensional representation and the infinite dimensional representation. So if you think about the statement, then now this was called the Zimmer's conjecture, and now it is solved by Brown, Fisher, Hurtado. And actually, let me just add one more statement. Maybe you can ask the dimension n-1 case, but now here actually you have an example, non-trivial group action of SL and Z on n-1 dimensional manifold. I will write down very soon. But if your manifold has dimension n-1 and assume that alpha of gamma preserve a volume, then actually you can get the same thing. But now there is an example that your SL and Z act on the n-1 dimensional manifold non-trivially, but without preserving volume, that you expect as like this. So SL and Z acting on R to the n by matrix multiplication. And then now this will give you the action on the space of all lines in Rn, which is just Rpn minus 1. Right? Because the matrix multiplication preserves the line. So lines goes to line. So you can act SL and Z. You can make the action of SL and Z on the space of lines in Rn. And this is n-1 dimensional manifold. And if you don't like the projective space, then maybe you can go to the rays in Rn, starting from the origin. Then this is actually the sphere. And these are called the projective action. So somehow the additional assumption is needed in order to conclude that the group action is trivial. That means that the image is finite. Because there is an example, a very nice example, that is non-trivial action on the n-1 dimensional manifold. But now after this, one may ask that, OK, so low dimensional case, we are happy because we can classify all the actions. Basically, there is no non-trivial action. But now if you see the statement a little bit more, then actually the statement is not about the trivialness of the homomorphism. You can ask that, so you are in this statement, you have a homomorphism. Then basically, you can lift your homomorphism to the SL and R, and then you can classify using some algebra. So maybe now one can ask the following question. So now if you have a alpha from SL and Z to the diffeo group of, let's say, C infinite, and n is only 3, then can we build alpha using first algebraic action whatever algebraic action means, because this is just a mimic of the, this is just some analog question in here, because how can you classify all the representation of SLNR? You should use some algebra. So maybe there is an algebraic action. And because as I said a little bit, there, other than SLNZ, there may be some error term that is not appeared on here, but maybe you have a dense representation into the compact group. There are lots of co-compact lattices that admits the dense representation into finite dimensional compact Lie group. So maybe there is some such an error. So I want to add something. I want to consider as an error term, which is the isometric action. So this is just a question. So if you have such a non-linear action, so if you think about the homomorphism, then this is basically about the linear action on Rn or something like that. But then now, can you do the same thing on the non-linear action or infinite dimensional Lie group?
I'm not sure that I understood. When you speak about algebraic action, do you mean that you want to lift to SLNR or not?
No, I don't. Yeah, OK. So the part of the question is that what is algebraic action? So yeah, that's the reason I put the question mark. So I also don't know what is algebraic action right now, but definitely this should be algebraic action. Yeah, it's coming from the matrix multiplication. I will give you one more algebraic action, even though I don't know what is algebraic action, which is the following. SLNZ preserved the, again, if you think about the matrix multiplication, then it preserved the z to the n. So actually, this will act on n tori, which is Rm mod Zn by Tor automorphism. So yes, z to the n. Thank you. And then this is given by, if you have a vector and if you have a matrix, then this is given by just, again, the matrix multiplication. So I don't know what is the algebraic action, but this should be algebraic. So now, yeah, this is the breakthrough. So now we want to think more on the building algebraicity on the action. And actually, recently, there is a progress in this direction. So the theorem by Brown, Rodriguez, Hurst, and Wang says that I will be in the same setting, and then now I have a again the smooth action on the manifold, and now let's just assume that dimension of m is m-1. So on the dimension m-1, I should detect this kind of example, right? And actually, in dimension m-1, we can answer this question because they said that when either, of course, you may have the trivial action, or m is diffeomorphic to Rp m-1 or Sm-1, which appears on here. And alpha is smoothly conjugate to the projective action. So far, the statements are clear, or? So now it is called the Zimmer program. And there are really a lot of variations of this question. So the other one direction is that if your alpha preserve the geometric structure, then what happens? That's the one direction. And also you may ask that how about the G action? How about SL and R action itself? So if you have SL and R action, then what happens? So there are really a lot of directions in this program, but what? Okay. So, but one important feature in this question is that how can you put some algebraic structure on M? So if you see or some isometric structure. So actually in here, even though I wrote down this way, actually their theorems are about, indeed, in both cases, there exists smooth Riemannian metric G on M such that G is alpha of gamma invariant. So actually they showed that the action is isometric. And then if you know that the action is isometric, then now your alpha, so basically what does really this says that your alpha is coming from the gamma to diff in phi of M, but actually your homomorphism factor through the isometric group with respect to G. And then this is the finite dimensional compact Lie group. And then using the Margulis superrigidity, you can tell that this is finite. On the other hand, in here, they really put the homogeneous structure on the M. So one direction I want to say in this mini course is that how can you put some homogeneous structure on M and from just group action with some dynamical assumption. So, but now before going to some measure rigidity, I want to add one more theorem in this direction. So if you think about the action on the projective space, which is the projective action, or the trivial action, which is coming from the isometric action, then in terms of the complexity of the dynamics, it's really not complex. It's really somehow, there's no complexity on the dynamics. So for instance, if you think about the projective action, then usually you will get the Morse-Bell dynamics, which is just you have a repelling fixed point and the attracting fixed point. And then the isometric action is really isometric, so there's no chaos. So that means actually in terms of the entropy, I will not define entropy, but I think you already saw the entropy in Barbara's mini course, so I think I can use it. Alpha of gamma is 0 for every gamma. And same for there. And for me, what is the zero entropy means that your past determines the future. So if you think about the dynamics, then you will go like this. If you choose something like 2, 1, 1, 1, of course 2, 1, 1 is 2 by 2 matrices, but 2 by 2 matrix, but usual element in the SLNZ act on the projective space like this, and your past trajectory will determine the future. So there's no chaos or chaotic behavior at all. And now one more theorem I want to put is that on the direction of putting the homogeneous structure on the manifold, which is the following. So this is the work with Aaron and myself. So if you think about the projective space dimension n-1 or below, then you will get non-chaotic actions. So maybe you can ask that if your dynamics has some positive entropy, then what happens? And there is an example on there. So if you think about the SLNZ action on N-tori, then hyperbolic matrix in SLNZ acts very chaotically. So it is called anosophy diffeomorphism.
Sure. Yeah. In all the results, the manifold is compact.
Manifolds are all compact. without boundary. Yeah. I think, so after I state here, actually, I want to say one thing, because I think, I'm not sure, but if you ask any kind of question, then I think we don't know the answer with 95% chance. So non-compact manifold, I think we don't know at all. So for instance, SL and Z action on the Rn or Rm. Yeah. So yeah, I only care about the compact manifold right now. And now here, let's say I want to put that. I don't want to restrict my lattice in the SL and Z in purpose. So this is a lattice. And again, I have a homomorphism from gamma to the field group. And then now let's just assume that dimension of M is n. But now I want to also see the chaotic behavior. So assume that there exists gamma naught in gamma such that it has positive topological entropy. Then, actually, I want to say that first, the gamma should be SL and Z of the finite index and conjugation. So basically, if you have a group action, then I want to understand what is the group and then what is the manifold. So this will give you some sort of answer that we can read the group structure from the dynamical assumptions on the action. And second, and also, as I said before, now my interest is put some homogeneous structure on M. So now we have partial answer for that. So if n is n least 4, for some very weird reason, there exists open set in M such that U is homeomorphic to the n-tori mod F. Well, F will be the finite point, and F and actually in tori, if you think about the n-tori, then there is a hidden symmetry, which is the x to v to negative v, given by the negative identity. So you can quotient out by the plus minus identity. Then you will get the infratori, which has the double torus as the double cover. But there is actually an action on here, so I cannot avoid it. But F is finite. This is homeomorphism. So we can put some homogeneous structure on M. Yes?
Homomorphism is equivariant?
Let's say no right now. Yeah, no. For this one, no. Yeah.
Is it only homeomorphism?
Right now, yes, it's only homeomorphism right now. Yeah. We are working more, but yeah, I think right now the written document says that this is just homeomorphism.
Right. What is the Tn plus minus there?
Tn plus minus there is that plus minus is Tn modulo plus minus identity. Yeah. So this is the just quotient by the finite group. It can be manifold or overfold, yeah. But there is a way to.
Thank you.
So what happened at n equals 3?
N equals 3. Okay, so I will not answer. There is some very weird reason we can only do this for n is n less 4. So yeah. But now, so yeah, the one thing I want to say is that here actually there are really a lot of interesting questions. And as I said before, if you ask any question, then I think I don't know the answer with 95% of chance. So there are really a lot of nice questions. And for instance, what is it? So for instance, even in this kind of theorem, can you really classify the so-called Q rank of the lattice in terms of the group action? Or anyway, so there are some other many interesting questions. But in this mini course, I want to at least show you one tool that can attack 5 theorems I wrote on the board, which is called the measure rigidity. And if you see the statements, then there is no measure at all, right? So they are all about the group theoretic property or some properties on the action or making some homogeneous structure on the manifold. So there's no measure at all. And actually, yeah, I hope you are surprised a little bit because yeah. OK, that's fair. But OK, let's erase this one. So yeah. So it looks like there is no room for the measure at all. But in some sense, higher rank, which is n is only 3, will give you the additional regularity if you think about the measure. So let me give you the, so these are the introductions. So let me just start with some definitions. So I want to start with the suspension. So these are all about the gamma action. So now if you have a gamma action on some topological space, then this is quite general. But if you want, you can just assume that the X is manifold and the action is smooth. Then now discrete group, you will see later why discrete group action is not good, or why the continuous action is better than the discrete group action. So I want to basically make the continuous action, not the discrete group action. So I want to think about the G action from here. But of course, if I can just cook up any kind of G action on some random space, but that's not what we want. We want to keep some information about the gamma action on space. So what I want to do is the following. I want to think about G cross X. And then now I want to think about the left G action and right gamma action, which is given by the left G and right gamma as following: GH gamma inverse and alpha of gamma of X. Let's say alpha is the action map. I think I put various examples and exercises in my exercise note about the suspension. So it looks very weird at the beginning, at first, but this is quite convenient to work with. So if you want, you can see the exercises so that you can be familiar with this kind of concept. But now what's the suspension space? Suspension space is X alpha, I want to call it. This is quotient by the right gamma action. And if you see the left G action, then left G action commute with the right gamma action. So actually there is a natural G action on here. So G is actually given, if you think about the quotient space H comma X, then actually this is basically same as just left translation.
At your formula, is it alpha of gamma or alpha of gamma inverse?
I think that one should be alpha of gamma. Or right action, yes. This should be inverse.
Wait, no. I mean, you can say that it is the G times gamma left option.
OK, so exercise, fix it. So that it is the right action on gamma and then left action by G. I think there's only one way to fix this. So here are some reasons why we want to care about the G action, because the two themes in the two philosophies in these 5 theorems is are following. So first, the dynamical properties of alpha are mimicked by A or P invariant probability measure that project to R. So here, A, now I only care about SL and R. So A is diagonal matrices, and this is R to the n minus 1. And because n minus 1 is n list 2, so this is n list R2. And that's very important. And that's the reason why I call it as a higher rank. And P is actually the upper triangular group. And why do I care about the, so let's just think about this part first. So why do I care about the A or P invariant measure? Because if you think about the G as a SLNR, then SLNR is not amenable. So there's no, if you choose the one definition of amenability, then amenability really says that if you act on the compact metric space, then there should be an invariant probability measure. But SLNR is not amenable. So there's no reason why we can expect that there exists a SLNR invariant measure on the suspension, on suspension. So SLNR is too big. But if you think about the A, then this is amenable. And also actually the P is amenable. So you can easily find that there is an A or P invariant measure on the suspension. And what does it mean that project to R? If you think about the suspension here, then actually there is a natural fiber structure of X alpha. So if you have X alpha, then you can easily see that there is a equivariant, G equivariant projection to G mod gamma. So G acting on here by left translation, and G acting on here by just translation on here. So this is just surjection to the G mod gamma, which is G equivariant. But now your fibers are all same as X. So this is not the trivial fiber, trivial bundle. So this is not really product. So on each point you have a different X, but still the fibers are X. And if you think about a little bit, then your gamma action actually happens on the fiber. So your G action on the base is given by just left translation, which is homogeneous dynamics, G action on G mod gamma. But on the upstairs, your gamma action, the information about the gamma hidden in the fibers. So for instance, if you have a G mod gamma on here, and you have X on here, then if you move A, let's say P, to X to Y by some large element G, then actually on the fiber, there is a corresponding gamma, which I called it as a return map in the exercise. Actually, your action on the fiber is given by some element in gamma. So your action, your alpha is encoded on the fiber. So I want to say that because R measure is very nice on the base measure, which is the G invariant measure. So dynamical properties of the action can be mimicked by some measure. There is a witness of the dynamical property, which is A or P invariant measure, because it is easy to find A or P invariant measure. And the really dynamical property sees the fiber. So this is one philosophy. And second, this is the main topic in the mini course, which is that under dimension or dynamical constraints, A or P invariant probability measure on X alpha project to R. On G mod gamma often exhibit the extra invariance or regularity. So I want to start with the measure on the x alpha, let's say mu tilde. That projects to har. Let's say har measure is g mod m g mod gamma. So if I choose the right measure, which is A or P invariant, and that mimics some dynamical property, and actually this is measured, but by the second philosophy, this measure should be very regular. You will see very soon, maybe on Thursday, you will see what I really mean the measure is regular. But basically, I want to say that your measure is somehow just measurable graph in some sense. But your measurable graph will be the smooth object. So that's the reason why in these two theorems you can build a homogeneous structure on M. Any questions so far? So far I think I did not do any math. This is just some philosophy. Yes?
So if the gamma action can be extended already to the g action on x, does the suspension is the trivial bundle?
That's the trivial bundle, and then action is just product action. Yes, and that's the one exercise in my exercise sheet. Yeah. Yes, good. So and also if your action is somehow the algebraic, so SL and Z action on Tn, then actually there is another way to build a suspension which is given by the homogeneous space. So yeah, well, you're right. So now in remaining mini course, we want to focus on here. And hopefully I can show you at least one or two, some sketch of the proof. How can you show the one or two of these 5 theorems assuming lots of things and then only focus on the second part. So yeah, there are lots of tools are used in these theorems, but these I want to say that this is called the measure rigidity because a priori it starts with the A or P invariant measure, but you will get at the end maybe you get the G invariant measure or some smooth object. Okay, so let's see. In order to explain what really extra invariance means, I really need to start with some foliation, dynamically defined foliations or laminations. So let's see. Can I do this? Good. So I want to introduce 2 foliations or laminations on the suspension. So this will be the 2 foliations or laminations that is defined by dynamics. So I will only consider the smooth action on the manifold right now, but this is real. Some of them are really general, so you can apply to the action on some locally complex and uncountable topological space. But let's just think about gamma action on M by diffeomorphism. M is manifold. And then now I have a G action on M alpha, which is the suspension space like this. So now your suspension looks like this and this. So now, first foliation is the following. You have and now let's just only focus on the SL3R. And now I want to say that U12, your U21 is the group, unipotent group given by this. And U31 is given by here. And something like that. And I think you realize that what I want to do. These are the root groups, right? So now what I want to do is that because you have a G action on the M alpha, and M alpha is very nice space, actually. Because if you follow the, OK, I erase it, but if you follow the definition, then M alpha is very nice space. So if you think about the subgroup U21 or U31, then actually there is a foliation given by the group orbit. So now I want to think about the x inside in M alpha. Then you want to think of, let's say, only focus on U12. Then this will. Oh, U12, yeah. But any combination will be fine. But yeah, one parameter subgroup. If you choose the one parameter subgroup, this will form the A foliation. And moreover, your leaves are very nice, right? So if you have x and OK, of course, these on the ambient space, this will be very weird. Your space of the orbit will be very, very weird. But at least the leaf itself, so the leaf itself is very nice. This is the C infinite leaf, which is basically R, immersed R, right? In M alpha. So this is the one thing. And then one good thing for this orbit foliation is that these are parameterized by U21, right? So there is a map from alpha, let's say the G action, let's say G action is always called alpha tilde, the suspension action, alpha tilde of U of x. And not only you have a very nice leaf, you also have a parameterization. So you don't need to parameterize the orbit again. So this is the one foliation, which is very nice. And the second foliation is not really foliation. It is really measurably defined and actually lamination in some sense. So now second, I need to introduce the measure. Say mu is the probability measure on M alpha. And assume that mu is alpha tilde of A invariant and ergodic. If you don't know the ergodicity, then that's fine. Right now, this is not really relevant, so let's just ignore. Alpha tilde A invariant, that means that for every A in A, alpha tilde of A of E has the same mass with E for a measurable set. So now, the ergodic theorem, the oscillator's multiplicative ergodic theorem, really tell you the following. So there exists lambda. Now I only care about the smooth manifold, so I can take a derivative. So lambda 1 to lambda k, which is actually the linear functional on Lie algebra of A to R. And this is linear. And there exists what? There exists the splitting. And actually, if you see the suspension, then this is a fiber bundle. And if you think about the picture on there, then there is an obvious horizontal tangent space, which is coming from the Lie algebra, right? So actually, you have a Lie algebra plus, I want to say that EF1, let's say F. No, let's write down E1, EL, and actually this will be G, the Lie algebra of G, plus let's say F1, F, I have K minus L. So there exists a splitting. But this is not continuous splitting. This is just measurable splitting. So this splitting only defines measurably. So mu almost everywhere. That means that there is a full measure set on M alpha such that you have a decomposition like this, such that, so let's say mu almost every x, let's say x, 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 such that first E I of alpha tilde of, let's say this way, d alpha tilde of A at x. And if you plug EI of x, then this will be same as EI of alpha tilde of A of x. So basically what I want to say here is that your splitting is invariant under the A action. So for every x, for every A, and mu almost every x. A of x. And moreover, actually, this is not only invariant splitting. Actually, you can, these are decomposed by the growth rate. So this is written as like following. So now, so I want to consider this is lambda 1, and this is lambda L. So there is a correspondence between this and this. So now lambda L plus 1 and lambda K. So I will only write down the the F first. But now let's say limit n goes to infinity, logarithm of growth rate, the alpha tilde of A. And if you plug V on here, and then if you put A on here, and then let's say A to the n, let's say A to the n, yes, n goes to infinity. And then now divided by n. Then this will be, because I have the here, so e to the lambda of, okay. Maybe I want to change the notation like lambda 1 to lambda L for this one, and then delta 1 to delta L, K minus L. Sorry, maybe this is better. So delta 1, lambda 1 will be here, lambda L is corresponding here, delta 1 is corresponding here, and delta K minus L is corresponding here. And this is delta J of A and for every V inside in F J of X. And again, for every A in A. So let's see, this is, yeah, log of A. I need to take the log of A. Yeah.
So do we need exponential?
Exponential of here.
Since we already exposed it, took log.
Took log.
On the left hand side.
On the left hand side.
I do see log.
So let's see.
Right hand side should just be delta J log n.
Delta J, yes. Good. Yes. So yeah, this is quite complicated as it is written. But what I want to say here is that on the tangent space level, you can decompose your tangent space into some invariant subbundles. Of course, it is only defined almost everywhere. But you can really distinguish your subbundle by the growth rate. That's what I'm saying. And actually, if you think about the tangent space of M alpha, then this comes from the horizontal, which is the Lie algebra of G, which is the tangent space of the G mod gamma. And this is that can be canonically identified to the verticals. So you have actually the vertical tangent space, which comes from the tangent space of M, and horizontal tangent space coming from the G mod gamma. And actually, you have the same property for the EIs, but you can easily say, actually this is another exercise, your lambda 1 to lambda L will be the exponent for the E1 to EL, which is on the Lie algebra of G, and this comes from the G action on G mod gamma, and actually these are the roots. So on the tangent space, your growth rate is given by the roots. That's one thing you can check. And these are the fiber-wise growth. If you act by A over and over again, then how your vertical vector growth on here, this is given by some linear functional. Okay, so I think you will see some more exercises later, but I just want to mention one thing here. It looks like this will not give anything about the manifold level. This will be about the tangent space level. But now how can we, because I want to say something about the foliations or laminations on the manifold, so I need to go to the manifold level. This is only on the tangent space level. So this is called the stable manifold theorem. But the theorem or fact,
we can delta 1 to delta k minus L the same?
Maybe they are same. Yeah.
Also, is k bigger than equal to L or something?
So yeah, actually, yeah, k is always bigger than L because you always have the root on the base. And then actually the number will be depend on the growth rate on the vertical. So k minus L should be at most the dimension of M. Because the sum of each dimensions will be the sum of the dimension of M. So yes.
Where does the lambda I appear anywhere?
So I did not write down one more line. The one more line will be d alpha tilde a to the n v when your v is on the ei. Then it will be the lambda. Yeah. And here's the last statement I want to do it today, which is that let's say L is the all possible exponent that appears on here. This is called the Lyapunov spectrum. And then now if, let's say, chi, the lambda, so let's say choose chi inside in L, and then define chi is lambda inside lambda or beta inside in L, such that beta is positively proportional to the C. They are linear functionals. So there is you can really multiply some positive number, and this is still linear functional. So I want to call this is the coarse Lyapunov exponent or functional. And then the fact is that for this kind of equivalence relation, this is the equivalence relation. So there are maybe everything are all not positively proportional. So maybe you have a k different coarse Lyapunov functionals or exponent, or maybe there is only one. Of course, there is not one because they are all not positively proportional. So maybe they are all positively proportional. Maybe. So I don't know how many coarse exponents will be appeared, but if you collect all positively proportional Lyapunov exponents or functionals, which is on element in L, then actually there exists mu almost every x, there is an immersed manifold like here. So this is, if you choose almost every point, then actually you can find a immersed leaf on the manifold. So I think I will start from here next time, and this is somehow okay. At least I can say one more thing, which is that because this is immersed manifold, I can think about the tangent space, and the tangent space is exactly the sum of the tangent. The invariant subbundle we found there. So E beta, where beta is inside in chi. So this is only about the tangent space level, but somehow, very surprisingly, you can find the corresponding manifold on the corresponding immersed manifold on the M alpha, such that you have a tangent space as the sum of the corresponding invariant subbundle. And actually, this is the A invariant.
Only E or E and F?
E and F, yes, sorry. E and F. Or F. I think that was a bad idea to use the f. But yeah, E beta or F beta, that depends on the number. So okay, I will start from here again. Maybe I can give you more clear statement on next time. But yeah, this should be the tangent space, the invariant subbundle that you can imagine on there, because each Lyapunov exponent will correspond to the one invariant subbundle, and then I want to sum everything.
The manifold will exist only locally or like globally?
See, this is a globally. So there is and these kind of manifolds are immersed RK, or are of some dimension.
But won't that get like folded out and become dense inside?
Yeah, maybe it is dense. I don't know. Maybe even it can be very, very short. Maybe it has something like you have M alpha like this, and then you have X. Maybe your manifold W chi will be maybe very, very long. So then maybe it is dense. But maybe at some point it is very long, it is dense, but maybe at some point it is very short, so you can only see the very short immersed RK. And maybe at some point maybe you have a large curvature, so that maybe it is very, very wiggled. So we don't know. We cannot control the geometry of the manifold, but still at least we know that this is immersed R to the dimension of the bundle. But here the one last sentence is that this will give you the some foliation, not really foliation because it is only defined almost everywhere. But one different thing with the orbifoliation, this is very nice, right? There's no parameterization, natural parameterization. And this is because I think I will not go there, but that's the reason we want to consider the normal form theory in order to parameterize this. But anyway, yeah, that will not be relevant. I think I can stop here, and then next time I will start from a little bit more on there, and then go to the measure rigidity.
Other questions for Homin?
What is known in low regularity for like Zimmer's program, like
low regularity? I think. Let's see. So
even say just a continuous action on for the manifold.
Continuous, I think we don't know, okay, unless it is circle. Circle is given by the Darrow and Hurtado, but other than circle, homeomorphism, I think we are quite, we don't understand very well. But I think the C1 low dimensional case we know. But even C Lipschitz, we don't know.
Okay, because you need the derivative.
Exactly, yeah.
Okay. Thank you.
Your question? Great. Let's thank Homin again.